All right, so our first speaker of the session is Pritish Kamath, and he's going to talk about how private DP-SGD implementations are.
Okay, thank you so much. Yeah, great to be here back in Boston. So this talk is about like revisiting the DP-SGD algorithm, and this is joint work with Lynn, Buddy, Ravi, Poisson, Amir, and Chuan, and we are all at Google Research. So I don't need DP needs no introduction here, but just very quickly, I'll be talking about like epsilon delta DP, where two algorithms, a mechanism is said to be epsilon delta DP if the output of the distribution on two adjacent data sets is closed in an additive and multiplicative sense for any event. So one important thing that I need to define here is what does it mean for two data sets to be adjacent, and I will defer that to later. Okay, so I'll get back to it. So this work is about revisiting this like very celebrated, very influential paper on DP-SGD as applied to deep learning. Of course, there were previous works which studied doing stochastic gradient descent with noise, but this is the one that was sort of pioneered the application to training deep learning models with DP. And so the starting point for this algorithm is that you have a differentiable loss, and you have an initial point, and you have an optimizer. So for now, we can just think of the optimizer as a simple gradient update step where you take a step in the direction of the negative gradient. And the most important ingredient here is, of course, the training data. So you have n training examples, which are arranged into like two batches. Each batch is of size B, right? So just to define the DP-SGD algorithm, let me recall the SGD algorithm, like the mini batch SGD algorithm, where, so this is an iterative algorithm where at each step, you compute the gradients on all examples in the batch, you average the gradient and then pass it to the optimizer, which updates the state, and then you sequentially keep updating the state and return the final model state. So DP-SGD modifies this pipeline in two very simple ways. So the first modification is that after you compute the gradients, you flip all the gradients to have L2 norm at most a certain predetermined value. Okay, and then you average these gradients and then you add Gaussian noise. So the Gaussian noise is of scale like sigma times C, where C was the clipping norm, the norm at which you clipped, and sigma is referred to as the noise multiplier. Okay, and then you pass this noisy gradient to the optimizer, and you update the state, and again you return the final model state. So analyzing the privacy of DP-SGD is a bit complicated. There's this non-convex loss, there's less clipping involved. So just to keep things simpler, it has been like the way DP-SGD is analyzed is by viewing it as a post-processing of this mechanism that I like to call adaptive batch linear queries. So it's the simplified mechanism, and it'll be easy to immediate to see that DP-SGD is a post-processing of such a mechanism. So you have this batch sampler, which arranges your data set into batches. So T batches, each batch of size B. So I'll be thinking of a single epoch here. So single epoch means that the number of examples is batch size times the number of batches. And now the adaptive batch linear query mechanism has this adaptive query method A, which based on previous answers comes up with a linear query. So a linear query is something that maps examples to unit vectors or vectors with norm at most 1. And then you compute the sum of the value of the query on all examples in your batch and add Gaussian noise. So you can think of this query as really this gradient oracle. Right? It's computing the gradient on the current iterate. And it's adaptive because the the point at which you query the gradient depends on the previous iterates. Now this adaptive batch linear query method returns all the answers, like answers to all noisy estimates of all the linear queries. So, and why is that? Because when you're faced with a non-convex loss, you can't really control how much information the last iterate has about all the previous iterates. So, sorry, did you say 10? I have, I'm 10 left. Okay, yeah. Okay. Yeah. So since you cannot control how much information the last iterate has about all the previous iterates, it's just pessimistic to just say that, okay, let me just analyze the privacy of releasing all the answers. Okay, so the main question we want to ask is, how does the privacy cost of this mechanism depend on this batch sampler? So to emphasize that, I've added the subscript of B. To emphasize the role of the batch sampler. So what kind of batch samplers am I talking about? So the simplest one is the deterministic batch sampler, where you just have your data you go through your data in the order it is given and just partition it into batches of size B. Okay, that's the simplest one. And intuitively, like you would imagine that adding some randomness to the batch generation process can help with privacy, right? And this broader phenomenon of privacy amplification. So a common batch sampler that is used is simple like shuffle. So you apply a random permutation on all the examples, and then go through them sequentially and partition them into batches of size B. Right. So some form of shuffling is commonly used in practice, but it's a bit hard to analyze the privacy of this because there is a correlation between the batches, right? If an example is in one batch, it's not in another batch. So for this reason, it has been common to instead consider this Poisson subsampling batch sampler. So here, each batch is sampled independently by including each example with probability of B over N. So each example is independently added with probability B over N. So you get an expected batch size of B. So now the batch size is not exactly B, but just to keep the comparison fair, I will still stick to this like B over N to be equal to 1 over T. So that like the number of examples is still expected batch size times number of steps. Okay. So there has been this gap between implementation and privacy analysis, right? So implementation is usually some form of shuffling. The privacy analysis is for Poisson subsampling. And this goes back to the original paper of Abadi et al., which talked about DP-SGD for deep learning. So it said that in practice, for efficiency, the construction of batches and lots is done by randomly permuting the examples and then partitioning them into groups of appropriate sizes. But for ease of analysis, we'll assume that each lot is formed by independently picking each example with certain probability. So there was this implicit, perhaps, understanding that these two processes are probably similar in terms of privacy analysis. So let's just make this simplification. But this gap has remained and has been recognized. And this nice survey by Ponomareва et al. Points this out, that there has been this gap, and it would be nice to have like analysis for shuffling itself. But in the meantime, since we don't have analysis for shuffling, at least it recommends that everyone be upfront about how we are processing the data and how we are reporting privacy parameters. And if you use this TensorFlow privacy method called compute DP-SGD privacy statement, so you give it all your parameters of your training, and it'll print out the statement, and it will remind you that Poisson subsampling is not usually done, but it's believed that the privacy analysis is close to that of shuffling, or at least better than like whatever you're doing is probably closer to Poisson subsampling than the arbitrary, like deterministic data order. And finally, I also want to point out that the Opacus library in PyTorch supports Poisson subsampling precisely because it is needed for DP-SGD. So before I get to the results, let me get back to what I promised you earlier about what is the notion of adjacency that I'm talking about. So typically, the notion of adjacency that is used is add remove, where you say that two data sets are adjacent if they differ on one example. Sorry, you can get one from the other by adding or removing an example. And this is the typical analysis, that is typical adjacency that is used for Poisson subsampling. But this adjacency does not make sense for deterministic or shuffle, because you require that number of examples is batch size times number of steps. So it's not compatible. So it just does not make sense. So an alternative is to consider substitution, where you say two data sets are adjacent. If you can get one from the other by replacing an example. So this is compatible with everything, but this is not the standard analysis for Poisson subsampling. So for here, I'll be focusing on this zeroing out adjacency. So this is introduced by Kairos et al., where they say that two data sets are adjacent if you replace a real example with a ghost example, and the ghost example always has zero query values or zero gradients. So the advantage of this adjacency is that the analysis for Poisson subsampling is identical. And now it also makes sense for substitution, shuffle, and deterministic. And of course, you can use group privacy to try to get bounds for substitution, but I won't talk about that. Okay, so let's get to what our results are. So for any batch sample, let's define epsilon b of delta as the smallest epsilon for which the adaptive batch linear query method, with batch sampler b, satisfies epsilon delta dp for any adaptive query method. So here's a simple plot of epsilon versus the noise scale sigma for a fixed delta and fixed number of steps. So I don't mention the number of examples and batch size because that's not relevant for the calculation, since I'm looking at one epoch. So this deterministic batch sampler is equivalent to a single Gaussian mechanism, and this is like very well understood, like nearly closed form expression. So you can plot this. So the Poisson subsampling batch sampler is also very well understood. So there is this like Renyi DP method. Ilya is here. So using this Renyi DP method, you can prove upper bounds on the delta for epsilon and epsilon for delta. And it was originally called the moments accountant in Abadi et al. Paper. And let me put a plug here for the Google DP accounting library, which has the implementation for doing this computation. Of course, there are other implementations. Perhaps this is the original implementation because Ilya implemented it. So there's an alternative method for doing privacy accounting, which is this privacy loss distributions, which is a numerical method, which gives you both upper and lower bounds on the privacy parameters. And it gives you better than RDP bounds. And this is also supported in the Google DP accounting library, and there are other libraries for it as well. So what our result is a new technique for proving lower bounds on shuffle. So a priori, like it's not clear if we just look at this plot, where does shuffle sit like in the context of these two curves? And so what we have is a lower bound technique for shuffle. And it seems that for the key takeaway is that for small values of noise multipliers, there's not much amplification due to shuffling. For large multipliers, large noise multipliers, there is some amplification. So let me quickly tell you the proof technique here. So to establish a lower bound, I just need to tell you one adjacent pair and demonstrate a separation. So we look at this adjacent pair where on one data set, all examples except one evaluate to a gradient of -1, and the differing example evaluates to a gradient of 1, which in the adjacent data set is zeroed out. So this distinguishing these two distributions is we show is equivalent to distinguishing these mixtures of Gaussians, which are centered at the standard basis vectors and the 2 times the standard basis vectors. And to show a lower bound, it just suffices to find a distinguishing set that can establish this lower bound on delta. And the distinguishing set is actually quite simple. So we just consider this like the set where the max value, max coordinate is at least a certain value. And that's it. Like just this construction, if you just try different values of C, gets you that lower bound. So just to summarize where we are, so the key takeaway is that we need to be careful in reporting privacy parameters because there's not much shuffling, especially for small sigma. So where do we go from here? So one thing to do is like one thing that is missing is a tight privacy analysis for the shuffle because like we only have a lower bound and like we conjecture that the pair we construct is actually the worst case, but we don't have proof. And so an alternative could be to use Poisson subsampling. So the Opacus library does have Poisson subsampling, but I'm not an expert and I don't know if it can really work at scale. If you know, you can tell me your problem. Like by scale, I mean that, yeah, whether it can really handle data sets that don't fit in memory. And another alternative is to use methods that don't need amplification, like DP-FDRL or DP matrix factorization. So I'll end here. Thanks.
Okay, any questions for the speaker?
Oh, very nice talk. Did you talk about anything between the shuffling and Poisson sampling? Because Poisson sampling is about one iteration, right? For every iteration, you pick a random size mini batch, but you could also do sampling with without replacement by finding a random fixed random subset, right? So where does that line sit in between?
Yeah, that's a good point. So like you're talking about sampling without replacement, but each batch is independently sampled. Yeah, so there is a sort of concurrent work by Gautam and sorry, I forget all the authors. There's Thomas and two other authors where they actually talk about this. And that also has a problematic privacy analysis. And the reason actually is quite similar in the sense that when you have a fixed batch size, then the non-differing examples can leak information about the differing example, right? So in the example that I had, when all other examples had a -1 gradient, right? If everything was -1, then my gradient is -2 times the minus the batch size. But if it is 1, then so my point is that the non-differing examples are leaking information about the presence or absence of a differing example in a batch, which does not happen in Poisson subsampling. And so the sampling without replacement, each batch independently, also has a problematic privacy analysis.
Hello, Christian Leveter here. I'm one of the authors
Oh, yes.
you referred to.
Yes, sorry.
So sort of the long story short, for sampling without replacement with Poisson, if you're using the add remove relationship, is that you need to add exactly twice as much noise to get the same privacy guarantee. So that can of course be problematic, right? If you need to add twice as much noise, then you get worse utility. And for some parameters, you can have very differing epsilons, similar to what they show here. You can have epsilons with around epsilon 1 for Poisson sampling and epsilon 10 for sampling without replacement. One question about this paper then is, did you look at what happens for multiple epochs? Because you look primarily on these small sigma values, and this is also where we see a big difference for the settings we look at. When sigma is less than 1, then you can see these large values. So I'm not sure what happens when you have multiple epochs.
Yeah, thanks for asking that question. So we have a follow-up work where we do have analysis for multiple epochs. Again, it's a lower bound technique. So it's we can talk about it offline, but we do have that. Yeah.
Okay. I think we need to move on to the next speaker. So if you have further questions, definitely for any of the speakers, put them in the Slack, and the Slack's available and you can talk to the speaker there.